Chapter 3 in this course goes over two-dimensional kinematics. For this chapter, we're pretty much going to expand on what we learned in chapter 2 and just kinematics itself. Now, if you realize, we had a x component and a y component in chapter 2. In this chapter, we're going to put them together. And you'll see how, if we know that there's an object traveling in the x direction, but also in the y direction, it has a specific motion that we have to follow that comes with it. And from there, we're able to figure out the motion in total with all the equations that come with it and how to solve it for x and y and then together. But first, we have motion in 2D. So it's easily, a basketball in flight to the basket, driving around in a curve, jumping into a lake. Motion in the real world is very rarely in straight lines. Motion tends to follow curves or zigzag paths. For this kind of motion, we need to think in more than one dimension. We need to develop two-dimensional kinematics. So for both 2 and 3-dimensional kinematics are simple extensions of one-dimensional kinematics, which we learned in chapter 2. However, expanding our understanding to multiple dimensions is very powerful and will allow us to describe all sorts of motion in the world. So for here we have you walk, from your starting point on the very left side of this figure. You walk to the right 9 blocks east, and then you go 5 blocks north. That's basically what this diagram is explaining. And then the question at the bottom is, what is the straight line distance? So if you were to start from the starting point to your destination in one straight line, what would be the distance there? Because we know that if you walk 9 blocks east, then 5 blocks north, you walked 14 blocks. But there should be a difference between walking east and north, and then instead of going to straight to northeast. So to solve that, we need to be able to use this equation here, which is the Pythagorean theorem. And here you have your a squared plus b squared equals c squared. Now for here, if you want to solve for c, which would be in this corner here, this line right here, we have your a here, so a squared, this number squared, plus b squared, whatever this number is, and then that would be your c squared. If this square root was still on this side, it would be c squared. So here we know that we're using the 9 blocks east, so 9 squared plus 5 squared, represented here, so 81 plus 25. Square root of that would give us 10.3 blocks. So instead of going 9 blocks east, 5 blocks north, which we would walk 14, if we're, let's say, in a helicopter and we can go straight across this path, they would only travel 10.3 blocks. So you would still get from your starting point to your destination, but you would get there in a much shorter time. So all this comes together because we're talking about vectors. Remember that a vector has both a magnitude and a direction. The straight line path that the helicopter took was a vector because we know that along the path, how long the path was, 10.3 blocks, and which way it went, roughly northeast. In 1D kinematics, we use arrows to denote a vector. The length of the arrow represents its magnitude, and the direction the arrowhead faces shows the direction in the vector it's facing. In 2D kinematics, we can represent a path using 3 arrows. One for the straight line path between the 2 points, one for the horizontal direction, and one for the vertical direction. The horizontal and vertical arrows are the horizontal and vertical components of the straight line vector. We do this because the horizontal and vertical motions can usually be treated independently. In the previous example, how far a person walks east is only affected by her progress eastward, not by how far she travels north or south. So if we're talking about horizontal components, that's the only form of motion we are talking about then. If we're only talking about our vertical component, our vertical motion, that's the only motion we're talking about in that instance. Now we're talking about the resultant, the total motion, then we can incorporate both your horizontal and your vertical. So for here, this shows the motion of 2 identical balls. One falls from rest, the other with an initial horizontal velocity. Each subsequent position is an equal time interval. Arrows represent the horizontal and vertical velocities at each position. So we see that the red ball goes straight down while the blue ball gets a little bit of a horizontal velocity, and you can see the progression there. Each time it goes a little bit farther in the horizontal direction. The ball on the right has an initial horizontal velocity, while the ball on the left has no horizontal velocity. Despite the difference in horizontal velocities, the vertical velocities and positions are identical for both balls. This shows that the vertical and horizontal motions are independent. So no matter if you have a x or not, a horizontal component or not, your vertical component will be pretty much the same. So for vectors, understanding and working with vectors is a really powerful tool in physics. But before we can really use them to solve problems, we have to understand how they work. First, we need to define some terminology. Since a vector has both a magnitude and direction, but sometimes we may only know part of it, we need to develop symbols to help keep these things straight. For example, a car speeds past you on a highway. The velocity of the car is a vector. We usually denote vectors as bold-faced symbols, like so, for your V, or sometimes with a hat, the little symbol on top of this V right here. But in the case of the car, we know that its direction, but not its magnitude. So sometimes it's useful to break out the magnitude, usually in italics. So this italicized V from its direction, theta. So theta would more than likely be the angle here. So over here, displacement can be determined graphically using a scale map, such as this one from the Hawaiian Islands. A journey from Hawaii to Malacca has a number of legs or journey segments. These segments can be added graphically with a ruler to determine the total two-dimensional displacement of the journey. So each part of these segments is different, but if you're to take the total distance between them, obviously you can just do a straight line. That's still going to differ between all these segments here. So going back to the original figure that we saw, a person walks 9 blocks east, 5 blocks north. The displacement is 10.3 blocks at an angle of 29.1 north of east. So for this, we know that if we're talking about a map, yes, we can look at a map and see, okay, well, you have to walk 9 blocks east, 5 blocks north. But this is also the problem here itself. We can just simplify it even more. If we're able to talk about, okay, well, we're going to travel 10.3 units here. We're going to have a magnitude of 10.3 units. And we're going to have a direction, theta, a degree of 29.1. That's pretty much, that could be interpreted in any situation. So while, yes, we can have it this way, we can use the terminology here, the units, the direction, with pretty much anywhere in physics. So for here, we are trying to identify how there's 9 units here for A at 0 degrees, right? Because it just went on the X on a horizontal, and that's what we're trying to get at. While here, yes, we went east here and then north. We can interpret them a little bit simpler. You can say, okay, well, you went 9 units instead of 9 blocks in your horizontal component in your X component. Then you went 5 blocks north in your Y component. So you ended up going 10.3 units in total if you were to go from starting point to your destination at this angle here. Okay, we're trying to simplify it even further. But here, if we have multiple vectors, it seems much more complicated, but we can add multiple vectors together to find the resultant vector. Now, these 10.3 units would be your resultant vector. Okay, so we went from, you did 9 blocks east, 5 blocks north. So you could have traveled only 10.3 blocks to, okay, you went 9 units, then 5 units. You could have done 10.3 units. We're trying to simplify this a little bit better so you can pretty much interpret it any way you want. But with all of this, we are adding vectors. That's the root of this. We are adding your x vector here plus your y vector here, and that gives you this r vector, this resultant. So, here's a representation of adding vectors. We have our a vector here. This is independent from the problem we've been solving. So let's say we have an a vector here, then we have a b vector connected right to it. Then we have another c vector connected to that. Well, if we're trying to find the total resultant of these three, it would be from our starting point to our destination, right? So our resultant vector, our end vector, would be down here. Because here, and we're going to see those in a second, you are adding a plus b, and then you're subtracting this c vector. Okay? So after you do all that, you're going to find that your resultant is actually down here, from your starting point to your destination. Okay? Same thing here. This is pretty much the same graph here, but now we start off with the C first, but then we add the A to the C, and then we add the B to the combination of these two. If you notice, the resultant vector is still there. The graph does look a little different, but the resultant vector is still under your X at this angle theta here. This one's under your X at this angle theta. Okay? So the negative of a vector is just another vector of the same magnitude, but pointing in the opposite direction. So B is the negative of negative B. It has the same length, but the opposite direction. So this means that rather than trying to subtract the vectors, we could just add the negative. Basically, since we're talking about magnitude and direction, our B itself is the magnitude, but our negative is the direction. So this would be like saying negative C, because we know that the direction here is in the negative negative Y direction, I'm sorry. But we know that all of these have their own components, right? So a little bit more examples of subtracting vectors. If we need to subtract vector B from vector A, instead of calculating A minus B, we can simply do A plus the negative B, right? So we can say, okay, well, I have my A. This one's representing A here, 27.5 meters, right, at 66 degrees. And this is my B going in the opposite direction at 112 degrees, but in the opposite direction. So like they mentioned, if we're instead of us saying A minus B, we can say A plus a negative B. So A plus here, because it's tailed ahead, A plus the negative B here, and we know that our resultant is going to be from our starting point to our destination. So it's very important for you to know how to draw these vectors so you know exactly where your resultant should be. Okay, and this is a representation of what a negative B would look like. So like they mentioned, it's the same magnitude, just in the opposite direction. Okay, well, we can add vectors together to form new vectors. Why not break apart the vectors we have into their own components, which I mentioned earlier? We can simply get this A vector here and find out their AX and their AY. Now, if we know that putting together vectors have their own components, why can't we go backwards, right? So here, if we know our A vector, we can find our AX and our AY by using these equations here. Now, whenever you're solving these, you have to be very careful. They really do depend on where your angle is pointing at. So our angle here says that our AY should be across from it, and our AX should be right next to it. The resultant should always be between your starting point and your destination. But sometimes this angle can get switched around. And maybe not in the following chapters, but probably halfway through the semester, you'll see that happen. But for now, we're going to talk about our AX being in our X component and our AY being in our Y component. So we have our A. We're going to do A cosine, which is a trig identity, and times your theta. And that'll give you your X component. Same thing with your Y. A sine theta. That'll give you your Y component. And these are all still related by the AX equals, or AX plus AY equals A squared, which is your Pythagorean theorem. C squared here equals A squared plus B squared, right? Now we're just using the terminology in terms of vectors here. So here, let's go back to the original equation. We can say that our AX here, let's make sure that this works. If we know our vector here is 10.3, right? That's what we had solved. If we do 10.3 times cosine of 29.1, we should get this 9 blocks, and we do. Same thing for Y. We do A sine of 29.1, we get 5 blocks north. So they're interchangeable. We can go back and forth between these. So if you know your AX, AY, you can solve for your A. If you know your A, you can solve for your X and Y component. And your theta is also in here somewhere. For that, you need to know your AY and your AX, because to solve for your angle, you need to use this equation here. So the other two, if you look carefully, you only have your cosine and sine. This -1 here means that you're using your inverse tangent formula here. So for your angle, for your theta, you are going to use inverse tangent of your y component over your x component. And that's how you solve for your angle. So when we figured out the 29.1, if you want to, you can use the inverse tangent of 5 over 9. And that should give you 29.1. So all these are related back to math, you know. For your sine theta, you can use your opposite over your hypotenuse. And that like I said, it really just depends on where your theta is. So if your theta is here, you're going to use your opposite here over your hypotenuse, your long resultant vector, over your c. So this would be b over c. For your cosine theta, you're going to use your adjacent. That means right next to it. That would be your a over c. And for your tangent, you're going to do opposite over adjacent. If you notice, your opposite here over adjacent here is pretty much saying like your y over your x. So these are the equations that kind of relate everything to mathematically wise, at least, back to trigonometry. So for this figure, we have this long vector A plus this long vector B, and we know that they equal this vector R, right? And we're going to break down on how you get there. So we know that for each vector, right, there is a x component and a y component here. Because we know that they're both advancing in the x and in the y direction in some way, form, or fashion. So if you break it down, you have your ax stops around here, and your ay stops around here. And then you add your bx, which stops around here, and your by, which will stop around here. Okay? And again, all these should equal your resultant. So we go a little bit more. We know that, like I mentioned, all these should equal your components of your resultant. So we know that if you add ax plus bx, that should give you your rx, right? If we add these two, that should be how long our resultant is. And same thing for your y. If you add ay and by, that should be how high your ry is. Okay? So let's go ahead and add some numbers to it, right? Let's go ahead and say that our angle for our A is 20 degrees and our A is 53.0 meters. Let's say for our B, we have 34 meters and it's at an angle of 63 degrees. Okay? And our resultant theta is 36.6 degrees here. Okay? So now that we know, what our components are here, let's go ahead and break it down all the way. So this is a similar representation of this one, but now we actually have numbers. We have our x components for both, our y components for both, and that way we can solve our x components for our resultant and our y component for our resultant here. Remember, you can use your cosine and your sine equations to solve for each one of these components. So we do 53 degrees or 53 meters, cosine of this 20, that'll give us a 49.8. 53 sine of 20, and that'll give us 18.1. And then same thing for your b component here. Your 34 cosine of the degree and 34 sine of the degree. So once we have all this broken down, we know that ax is 49.8, bx is 15.4. both of them are in our x direction, so we can go ahead and add them together. And our resultant x would be 65.2 meters. Okay, because they're all together here. They're all in the x direction here. We can do the same thing for the y. We know our AY is 18.1 and our BY is 30.3. We add those together, we get 48.4 meters. Okay, so if we do the Pythagorean theorem, a squared plus b squared equals c squared, we can solve for this 81.2 meters. We'll do 65.2 squared plus the 48.4 squared, and then we're going to have to square root that entire thing. And that'll give us the 81.2 meters. And of course, you use your inverse tangent to solve for your degree. Right? You do inverse tangent, right? Because that's our equation for our degree of 48.4 divided by 65.2. And that gives us the 36.6, which was already included to begin with here. Here they omitted it out, but that would be the entire process here. So if you are able to break down each vector to your x components and your y components, you can go ahead and solve for your r component here. Okay, so subtracting vectors is basically the same thing. We have our a, right? And then we're going to add, remember, we're adding the negative. So that means we're going to put and right next to our a component here. So our b component goes downwards, sorry, and that'll give us our resultant. It's the same thing. We can go ahead and break them down to our ax and our bx, right? So, this is a different one. We can go ahead and break them down to our ay, by, ax, bx, and follow the same process. Same thing for this one. Even though they're facing the opposite direction here, we have our ax and ay, bx, by with their respective degrees. It says here is 30, here is 45. This one's below the x. So if we're doing all this, we know that our resultant is going to be connected between these two, right? So basically, if we wanted to, we could rearrange everything here and get them all in the same quadrant system. So we have our ax, by, or ax, ay, bx, by, and that'll give us our rx here and our ry here. But it's basically the same thing. Instead of starting at this point somewhere in this quadrant here and ending over here, all we're doing is putting it all together in this quadrant here. That way we're not crossing quadrants and we're not starting from, a negative, let's say 4 over here and then stopping at a positive 5 here. That way it's all together. We know that all of our numbers are going to go from 0 to wherever this ends up. And it's a little bit easier to read. So for all this to make sense, to bring it back to physics, this is called our projectile motion. Okay? Because we know that, like we mentioned at the very beginning of this chapter, not everything is in one dimension, and almost nothing is for us here. So we know that if you throw a rock off a cliff, we know if you throw it horizontally, it's eventually going to go down, right? And we saw an example in chapter 2 on that. But for projectile motion, it looks in two directions at once, both in the horizontal direction as well as in the vertical direction. Motion in these directions are independent of each other. Just because there is an acceleration in the vertical direction, because there is gravity, doesn't mean it affects the horizontal direction at all. Here we see a ball dropped, in the pink, and a ball rolled off a table in the yellow. Since both balls have the exact same initial velocity in the y, 0 meters per second, because they were both at rest, then we can see that they fall at the exact same rate. So just because this one didn't move in the x direction and this one did, doesn't mean that they're not going to fall at the same rate in the y direction. Here's a little bit better representation of it. Let's say you are starting to throw this ball from 0x and 0y. Even though you throw it upwards here, right? You see these vectors slowly in the y direction kind of come to a halt here. There's only an x vector here, right? And then you see that once it's starting to come down, they get bigger and bigger here, right? So down here is a breakdown of each component here. So this is the horizontal component for each point. You see that that doesn't change almost at all. It stays constant, right? So each part here is constant. It's the same vector, the same direction. Where our y, we start off pretty high up, slows down a little bit, slows down a little bit, and comes to a halt here. And then we see that here it increases here a little bit more, and same thing here, it increases a little bit more. And for D, this is our x component and our y component. This would be what you would see whenever you realize, okay, well, my velocity vector, let's say, is 10 meters per second, and my velocity in the y component was, let's give this a -5. Okay, well, let me find out my resultant from your starting point to your ending point. So that brings us to our first example. Okay. We're going to pull it up on the textbook. So during a fireworks display, a shell is shot into the air with an initial speed of 70 meters per second at 75 degrees above the horizontal. So just as it shows here. So we know that, okay, off the bat, we're going to have an x component and a y component of this velocity, because velocity is a vector. The fuse is timed to ignite the shell just as it reaches the highest point above the ground. So for A, we're going to calculate the height in which the shell explodes. For B, we're going to calculate how much time has passed between the launch of the shell and the explosion. And for C, we're going to calculate what is the horizontal displacement of the shell when it explodes. Okay? So we know that for all this, we have our x components and our y components, right? But we know that here, by the highest altitude, if you think about it, once it's at the highest altitude, that means we're not going to gain any more direction in the y, correct? So that means at some point at that very hill, the very top, the very peak, the velocity component in the y is 0, right? Because it stops going upwards. So we're going to go and use this equation here. You realize that this is for your y component because you already incorporate your gravity here, correct? So we know that our y component, like we mentioned, is going to be 0 because it stops at that highest peak. And we have our initial velocity of the y component because we have our v sine of 75 we have to calculate. And we have -2 times our gravity times the height. And we are told that the height, let's see. Well, that's something we have to find out. Okay, so we arrange all this, and that's exactly what we're trying to find. So we know that our v initial, v naught, y needs to be our v initial sine of our 75 degrees. So 70 meters per second, that's our initial, sine of 75 degrees. And that gives us 67.6 meters per second. So we go ahead and plug that back in. We don't get rid of this squared because nowhere in this calculation do we have a squared. So that's independent of our component mathematics. So 67.6 meters per second, all that squared, times 2, or divided by 2 times 9.8. So we find that our height was 233. That is the highest peak that this firework is going to go. And at that point is when the explosion is going to happen. Okay. So for B, now we're going to solve for our time. So here, we're going to go ahead and we can use our equation for our y component still, because we just found our y component velocity, and we know our y component height, so we have the most information there. So we're going to go ahead and use our y equals y initial plus 1/2 velocity component in the y plus our velocity, or our initial velocity in the y plus our velocity at that point times time. Okay. So we know that our velocity y at that point at the highest peak is 0, because like we mentioned earlier, it stops at that point. So we know that this is already 0. This vy is gone. So once we arrange all this, we have to isolate our t. So we have to make sure that all the 1/2 and just the v naught y plus v naught or vy is divided on the left side here. So once we move everything over, you multiply the 2 to get rid of the 1/2, and then you divide the v naught y plus vy. We know that our vy is 0, so that's gone. So we only have our vy component from our initial velocity. That's what this v naught is. So we have our 2 times our height that we found, 233, divided by our 67.6, and that gives us 6.9 seconds. So between the time it launched to the time it reached the highest peak is 6.9 seconds. And for C, now we're trying to find our horizontal component. How far in the horizontal did this firework go? Okay. So for here, we have to use our, if this might look a little bit different. We initially have this equation here, but if you notice, this also equals our, one of the first equations that we used, which was V equals X over T. Rearrange, you can use X equals VXT. So here we still have to find our velocity in the X component. So Vx equals our initial velocity, which was 70 meters per second, cosine of 75. So that gives us 18.1 meters per second. Okay, that's our Vx. So once we know that, we know our time, right? Because that's the one thing about our two-dimensional kinematics. Time is independent of your components. The same amount of time it took for your X component to go the distance, go how fast it was, or whatever, is the same amount of time that it's going to take for your Y component to do. Our times are interchangeable. So we can go ahead and use that 6.9 seconds. You plug that into that equation, you do 18.1 times 6.9, and you get 125 meters. That's how far in the X direction this firework went. Okay. So for here, this problem you solved for your Y component in your distance, how high it went. You have your Y component of your velocity, initially and final. You solved for, like I mentioned, the height. You solved for your time. And you solved for your horizontal component. So here, vectors, if they're pretty much being used everywhere here. We have our X and our Y, height and distance. That's our displacement component. And we obviously have our velocity component in the X and Y. Okay. So for a horizontal range example, suppose that you hit, a golf ball at 36 degrees angle at an initial velocity of 55.6 meters per second. How far will the ball travel in the X direction before hitting the ground? So we can assume that the horizontal formula, but for this only works with the initial and final heights being the same. So let's say that, we throw a ball on a football field. We can use this equation, this particular equation here, for that example, when our horizontal or our initial and final heights are the same. Because we don't have to worry about anything else. So for this one, we're trying to find out we have our V naught, so 55.6 squared sine of our 2 times our theta, so 2 times 36, that would give us 72, over RG. You plug that in, and that will give you the exact answer you are looking for here. Okay, for our next example here, we have Kauai in Hawaii is the world's most continuously active volcano. Very active volcanoes characteristically eject red hot rocks and lava rather than smoke and ash. Suppose that a large rock is ejected from the volcano with the speed of 25 meters per second, so it's already a projectile, and at an angle of 35 degrees above the horizontal, as shown in the figure. The rock strikes the side of the volcano at an altitude of 20 meters lower than the starting point. So we automatically can't use this equation. Calculate the time t it takes for the rock to follow this path. So we know here's our starting point, here's our destination. Okay, so we have to solve how long this is going to take for the rock to hit the ground. Okay, so we're going to go ahead and use this equation for this one because we have our time, we have our gravity, we have our initial y component, or initial height, and we know that it lands 20 meters below where it started, right? And obviously, if it's taken off at 25 meters per second, we have our velocity. The only thing we're solving for here is our time, right? So we plug everything in. We know that the final v, or the final y, I'm sorry, is negative 20. We know that our initial y here was 0. That's what we're going to take it as. We have our velocity component in the y. That gives us 14.3. Once you do this here, solve for your v in the y, 25 meters per second, sine of 35, minus our 1/2 g, 9.8. So 1/2 times 9.8 gives us 4.9 t squared. So we still are looking for our t. Now, for these types of problems, we are going to have to use our quadratic formula. Basically, what we're going to have to do is solve this in a form where you have your value, I guess you have our a squared, our t squared, then the value itself is by itself, so t, and then where your value is non-existent in the last component, and all that has to equal 0. So basically, if in mathematical terms, we have our a squared, or our a t squared plus b t plus c equals 0. So each a, b, c is what we're going to take from here. Okay, and this is strictly math. This isn't something that is taught here in physics. It's just one of the tools that we use in here. But if we look between these formulas here, we can pretty much know what our a is. Our a is 4.9. Our b is negative 14.3. You got to take the negative. And our c is negative 20. So we know our ABC, and we're going to plug it into this equation here. Okay? So once we plug in, we have our negative 14.3 plus minus square root negative 14.3 squared minus 4 times 4.9 times negative 20, all over 2 times 4.9. So this equation gives us actually two solutions. One which is 3.96 and one that is negative 1.03. Now, does a negative time make sense? Not exactly, right? Doesn't make sense for anybody or anything to have a negative time. Can't go backwards. So we're going to take the positive value here. Now, this is one of those things where you have to be careful. You have to make sure that your answer makes sense here. Now, if I was to take the negative time and plug it in, I could get a value. I could get an answer, but it would be the wrong answer because it doesn't make sense for us to have time. So we're going to go ahead and take 3.96 here. Okay, and that's how long it takes for that rock to hit this point down here. Okay. So our launching angles, trajectories are projectiles on level ground. We have the greater the initial velocity, the greater the range for the given initial angle. So if we have 30 meters per second at 45, we're only going to go this far. If we have 40 meters per second at 45, we'll go this far, and so on and so forth. It really does matter what your initial velocity is here, because the greater the velocity is, the greater you're going to go. Now, the effect of the initial angle on the range of the projectile with a given initial speed is indicated here. Note that the range is the same for initial angles at 15 degrees and 75 degrees, although the maximum heights of those paths are different. So just because, okay, well, we have, 50 meters per second here, okay, well, that one's kind of shorter than this one in the X, but, it's higher. And then this one's actually longer than it was over here. So it really does matter what your initial velocity and what your angle is. Okay, and we've noticed that in a couple of examples here where our degrees are a little bit higher or lower, which kind of makes our velocities in the x and in the y direction higher or lower. So it does, change everything. Okay, so for this one, I noticed that this one wasn't in the textbook, so I went ahead and wrote everything out. So suppose that you want to drop emergency supplies out of a helicopter to a stranded hiker. If the helicopter is moving at 200 meters horizontally above the ground at a constant 70 meters per second, how far away from the hikers in the horizontal direction must you be when you drop the package so that the package lands where the hikers are? Okay, so basically you have your own trajectory here. You are in the helicopter, you're trying to drop some supplies to these stranded hikers, and if you drop it right above them, well, that's not necessarily going to go straight to them. That's going to go at a distance. So we're trying to figure out how far in advance do we have to drop them to actually get the supplies to the hikers where they're supposed to be. So I went ahead and drew this x and y t graph. I've noticed that it's easier to, I guess, figure everything out, know where everything is at if you separate it between your x and your y. So if you're able to do that, you'll notice that we have our horizontal component here as 70 meters per second in the x because it's only moving in the x direction. It doesn't say that the helicopter is going up or down. Okay, so we can assume that our velocity in the y is 0 because we're not moving in the vertical direction. We know that it is 200 meters above the ground. So we know that our y initial is 200 meters above. And obviously we know our acceleration here, 9.8, negative 9.8. So what we're going to do is use this equation here. Our delta y, which is just our change in y, is equal to 1/2 at squared plus v initial in the yt. But we know that our initial velocity in the y direction is 0. Like I said, the helicopter itself is not moving up or down. So we can go ahead and cancel that. So we have our change in y is negative 200 because the supplies are going to go from 200 meters above the ground to 0. So 0 minus 200 gives us negative 200 equals 1/2 times negative 9.8 t squared. So we have 1/2 times negative 9.8 gives us negative 4.9. Divide both sides by the negative 4.9 because we are trying to isolate this t. And once we do that, square root both sides, you get 6.39 is our time. That's how long it takes for the supplies to drop down to the hikers. And the reason we're finding out our time, because that would help us figure out exactly how much longer before we have to drop them. Now, like I mentioned, time is interchangeable. If we have it in the y component, we can have it in the x. So initially, in the x component, we kind of didn't have anything besides our velocity. We didn't have our x. We don't have an acceleration. We don't have anything. But now we have our time. If we have our time, we can go ahead and use this equation, one of the first equations we solved, and we're able to find our x, which is 447.3 meters. That's how far before the actual drop site we have to drop the supplies so they can actually reach the hikers. Okay? So if you're able to find your time, you can pretty much figure out what distance before the hikers you can actually drop them. Okay, so we also have our relative velocity, which is basically something we incorporated in this last example. So we know that if you're trying to drive or trying to float down this river, you're not actually going to go straight down the river. You're going to go at a certain velocity down the river. So while to us, if you're actually on the boat, you'll seem like you're going straight across. But to somebody, that's on shore, you're going to be going in this diagonal, right? So let's say for here, the river's going this way to the right. So if you start off here, well, you're going to go straight, right? You're thinking you're going straight, but you're actually going at this angle because the flow of the river is pushing you slowly this way. Same thing here. If you're in an airplane, you're thinking you're going north, well, you're actually going a little bit west, depending on the wind speed. Here, the wind speed's a little bit to the left, so obviously it's going to try to push this airplane more to the left, more to the left, more to the left. Now, it's kind of hard to, imagine this, seeing an airplane from the ground, but this is actually true. It's kind of the same representation of, being on a boat. Just because somebody in the airplane doesn't feel the shift to the left or to the right doesn't mean that it's actually not there. Okay, so for the velocity here of an object traveling at an angle to the horizontal axis is the sum of the components Vx and Vy. Same thing we've been talking about. We have our displacements that we have our vectors, we have our velocities that we have our vectors, and we actually have our accelerations that have our x and y components as well. But for this one, we've mostly been talking about our velocities. Okay, so going back to the example of the boat, we have a boat attempts to travel straight across the river at 0.75 meters per second. The current in the river, however, flows at 1.2 meters per second to the right. What is the total velocity of the boat relative to the shore? So we're trying to find the velocity of a person standing down here, waiting for this boat to cross. Okay, here we go. So we know that our velocity in this direction, we'll call this our y direction. It's always important to denote which one's your x and which one's your y. We know that our velocity in the y direction here is 0.75 because that's the velocity of the boat. But we also know that the river is trying to push it to the right at 1.2 meters per second. So we need to find our resultant here. We need to find how fast it's actually going, in total, our resultant. So we do that ax squared plus bx squared, or a squared plus b squared. Okay. So here, all they're doing here is trying to denote which one's which. So we know that because we said our y direction's upward, our x direction is to the right. We know that our velocity in the x component is the river. Our velocity in the y component is the boat. So we put that together. We find out that our velocity is actually 1.42 meters per second. That is our resultant here. So because we have our y component and our x component, we can also find our angle, the angle that the boat's actually traveling in. We do our theta equals our inverse tangent of our y component over our x component. So we plug in our 0.75 for our y component, and we plug in our 1.2 for our x component, and that gives us 32 degrees. Okay, so it's traveling at 1.42 meters per second at 32 degrees relative to the shore. Now, if you're in the boat, you probably won't feel the river velocity. You probably won't even see the degrees. So it really depends on where the observation is taking place. Okay. All right, and back to the airplane as well. We have an airplane is known to be heading north at 45 meters per second, though its velocity relative to the ground is 38 meters per second at an angle west of north. So we're taking our y and x, our y to be north, our x to be east. So we know that if east is to the right, we are going west to the left. So that's why the resultant here is to the left. What is the speed and the direction of the wind? Okay. So for here, same thing. They're trying to denote which one in particular is our x component and which one in particular is our y component. Well, we know that the plane is trying to go north, right? But we know that the speed of the wind is trying to push it to the left. Now, our wind is strictly to the left, right? So that's in our y. V of the wind in the y component. Okay. And we also have our V of the wind in the x component here, trying to push it to the left. But our velocity of the airplane is going north, strictly north. Okay. So for here, we are trying to find our total. We can use the first of these two equations to find our vx of the wind. So if we do that, we can find our velocity total is 38 meters per second here, which is the resultant vector. And because we know that our v of the airplane is in the y direction completely, we have our wind direction to account for. Our wind direction here is negative 13 meters per second because remember it's negative. It's going trying to push it to the left. It's trying to push this whole airplane to the left. Okay. So our v in the total and the y is our v of the wind and the y plus our v of the airplane. Okay. We put all this together. So the v of the wind would be our v of the wind in the x plus our v in the wind of the y, 13 negative 13 squared plus negative 9.29 squared, which we solved here from our v total in the y direction. So our v of the wind is 16 meters per second, and you can solve your angle as well. So for this one, the tricky part is just trying to denote, okay, what's going north, what's going west. Okay, we know that the airplane is trying to go strictly north, but it's getting pushed. We know that that has its own vector here, as you can tell. This is your resultant. You have your y component, and you have your x component. Same thing with the wind. You have your wind, let's say it's pointing here to here, meeting right here. You have your x component, and you have your y component. Okay. So classical relativity, this actually has its own chapter in physics. The same motion as viewed by two different observers. An observer on the moving ship sees the binoculars drop from the top of its mast fall straight down. An observer on the shore sees the binoculars take the curved path moving forward with the ship. Both observers see the binoculars strike the deck at the base of the mast. The initial horizontal velocity is different relative to the two observers. So just because this person here is at the shore, he sees the binoculars fall at this rate, right? He sees it differently than the person who is actually on the ship. The person on the ship sees the binoculars just fall straight down, as indicated in this blue arrow here. The person on the shore sees the binoculars fall in this motion here. So it really just depends on where the observer is. Like I mentioned, this one actually has its own chapter way later on in physics and can actually be pretty confusing, but that's pretty much the gist of it here. So for our last slide here, we have the motion of a coin dropped inside of an airplane as viewed by two different observers again. For observer A, which is here, an observer in the airplane sees the coin fall straight down. For B, which is down here, an observer on the ground sees the coin almost fall horizontally, almost. So why is this? Well, we'll assume that an airline passenger drops a coin while the velocity is at 260 meters per second. What is the velocity of the coin when it strikes the floor at 1.5 below the point of release? So measured in relative to the plane and measured in relative to the earth. For these two, they're both going to be different. We're going to be able to notice that they're not really the same, but it really just depends on the observer. So if you're able to go through this one, let's see. Okay, so for solution A, using the given information, we note that the initial velocity and position are 0, and the final position is 1.5 meters. The final velocity can be found using this equation. So we go back to our y component velocity. Vy squared equals v initial of the y squared minus 2 times your change in y. Okay, so if we're able to plug all that in, we're trying to find our vy. We know our v initial is 0. We know our gravity, 9.8, times our change in position. We are falling from 1.5 to 0. So our velocity here is v of y is negative 5.42 meters per second. You got to be careful here. You have this squared at the very beginning. You have to square root this number here. And that's why those two differ. But you notice that it's negative. It is falling, right? But for B, we have, our initial in the x here was 260. It's something that was told in the problem, right? So an airplane passenger drops a coin while the plane is moving at 260. So that gives us our initial velocity in the x. Well, we just find our initial velocity in the y. Plug that back in, we have our velocity here yielding 260.06. And if we find our angle, it's actually at negative 1.19. So like I mentioned, being the observer, where the observer actually is, really changes the problem and the dynamic completely. So go ahead and go through this lecture, go through this chapter. If you have any questions, please feel free to contact me. Two-dimensional kinematics is one of the toughest chapters, I will admit, in college physics. So again, if you have any questions, do not be afraid to contact me.